what is the role of our piperidine in the traditional mechanism?
Isn't it a base? So
it acts as a base, correct. So what does it do?
So it removes the alpha proton from the diacid.
Yeah, so it removes one of these protons, yes. And then what happens?
It will form enolate.
Yeah, we have the formation of an enolate form. And what does the enolate do?
So the double bond attacks the aldehyde.
It attacks our aldehyde, okay. And at this stage we have usually, so we tend to use acetic acid in the reaction, so this negatively charged oxygen tends to get protonated, okay. And we have the formation of this sort of aldol intermediate, okay. Then what happens here? It should be quite easy to spot because
so proton transfer.
Loss of water.
And yeah, like
dehydrate the...
Okay, so we have our base. What does it do now?
So it takes the proton, the alpha proton, and then the double bond forms and you lose H2. Sorry, you make the enolate.
Right. And we have the formation of our product. Okay. So there's a reason why I wanted to discuss the Novenagel condensation, because you may or may not have seen this modified version of the reaction in the past. So can you tell me what happens if we use malonic acid instead of the ester and we reflux the reaction using pyridine as well?
So will pyridine go for the carboxylic acid proton rather than the alpha proton first?
Okay, well, we definitely have a more basic mixture, yes. So I agree that we will remove one of the carboxylic acid protons.
Will CO2 be released instead?
Okay, let's think about what happens step by step. Yes, but it's you said it correctly, Will. So did you see it already, or
no? It just reminds me of what we did. It just reminds me of what we did with Joel last year.
That's great. Okay, excellent. So if you have seen it already, you should be able to tell me everything that happens.
So now one of the alpha protons gets taken by a base, and then that forces the CO2 leave. So you like make the enolate, and then the electrons form the double bond, and then the CO2 leaves, I guess.
Okay, so we have the formation of this dianion, right? Which is also stabilized by the fact that it delocalizes this hydrogen with the formation of an hydrogen bond, yeah? So from here, what happens? We attack our aldehyde, as we have seen before. Not much of a difference here, okay? So we still have our protonated base, from which we can take a proton, and we are still in this situation, okay? Also here we have the formation of this sort of aldol intermediate. Now we can protonate this oxygen as well, thanks to our protonated base. And from here, what happens, guys?
Proton transfer to the... Oh wait, no. Yes, no. Does the proton, because you've drawn out that proton, so it must do something, I guess. Like transfer to the, so in the bottom right, it's had to...
At this point, guys, we have this spontaneous decarboxylation with this cyclic mechanism, okay? So we have the
Oh, you lose water as well.
We remove
Yes.
water, yes, CO2, correct, Bailey. I think you have said that we remove water, but I'm not sure. And what do we form, guys? In this case. So what's our end product here?
Beta unsaturated.
Yeah, the
Carboxylic acid.
the E alkene, okay? So the E alkene is associated with a more stable transition state for this reaction, and so we can selectively form E alkenes also with this version of the Venagel condensation. Okay, guys? So the reason why I wanted to refresh our memory on this reaction is that you should have noticed, and I had anticipated it already on Tuesday, that we have seen a few reactions this week to make alkenes selectively. So can you remind me, guys, which reactions we have seen to make alkenes selectively? Well, this version of the Venagel condensation to start with, and then
the Wittig.
we have seen the Wittig, yes, that you knew already from the last years. And then what else?
When you use like alar silanes, or
I guess, yeah.
Pardon, Will?
like when you do reactions like alar silanes.
The Peterson elimination, yes. So we have seen the Peterson elimination, that's one. I have it last in my slides, so this is why it is not appearing in this moment. Okay, Peterson elimination is one. Then what else? We have seen other two reactions to make alkenes selectively.
Is it the Julio olefination?
The Julio olefination is one of them. So we have seen that it is used to make E alkenes, but with the one-step version of the reaction, we can also selectively make Z alkenes, tuning the conditions. Okay, so we have Julia, we have the Peterson elimination. We have seen another one.
Swern.
There's one with borons as well, wasn't there?
Well, yeah, I didn't include it here, but with the one with boron, we have seen the hydroboration oxidation, where we use alkenes, okay? But I'm thinking about something that uses a sulfur instead.
Oh, what, like the enone one? Or I suppose that,
That one, Jack, yes.
Elimination,
So
oxidation.
Yeah, the elimination, oxidation, and usually we make E alkenes unless we have a cyclic starting material, okay? Okay, so here comes also the Peterson elimination, which again can be used to make E or Z alkenes, depending on the conditions that we apply, so basic or acidic, and the starting materials, okay? Okay, so this was just to recap a little some important reactions we have seen this week. Now, let's start with the first real exercise for today. I would like you to tell me the product of this reaction. Thinking about what happens step by step.
So is it going to be intramolecular aldol?
It is going to be an intramolecular reaction. Yes, yes, yes. So what do we have that happens first? So we are starting from this.
So we make the enamine with the ketone.
Okay, we make the enamine with the ketone with which one in this case, in your opinion? Where
The
our-
leftmost one, the
Yes,
The more
stretching.
isolated
exactly,
one.
because it is the least hindered carbonyl group. Okay. Okay, so from here we have this situation, right? And in the end, we form what?
So it eventually makes an enemy.
So yeah,
Yes.
you lose water.
We make an enamine. Yes, that's
So
correct.
then, yeah, double.
Yeah.
Okay.
So we have our iminium ion first, and from here we make the enamine. Okay, so that's the first thing that happens in this case. Very good. Now we are in this situation. So we have made our enamine. What do you think may happen here, guys? I have highlighted for you something that is important.
So eventually the highlighted oxygen coordinates to the proton of the carboxylic acid.
Not yet, not
Would-
yet.
would
We have
the-
something else that happens first.
Would the nitrogen lone pair come down and the double bond attack the carbonyl, the pink one?
Yeah, that's exactly what happens, Will. So in this case, we have a selective attack on one carbonyl only, okay? So we have a selective attack here, okay? And we have the formation of the 6-member transition state you have seen in the video, which I will never ask you to draw.
Yeah, I can't
Okay?
draw it.
So
Yeah, it's
I
pretty
wouldn't,
hard.
Yeah, I can't
I
draw
wouldn't
it. No.
ask, so I wouldn't ask you anything like this for the exam, for example, okay? But it is just that we should try and get familiar with these kind of reactions and with how they work, okay? Anyway, we have this situation here, okay, where we have this methyl group which is pointing towards us, so it is in front position, and we have this group here at the back, okay. So if we now rotate this transition state that we have, we obtain this situation here, okay, from which we release our iminium, okay, guys. And from here we can easily hydrolyze. So we remove our imine and we remove our proline organocatalyst with the formation of the product of the reaction, okay? Plus, of course, proline, which gets recycled. So I wouldn't ask you anything like this for the exam, but we should, let's say, at least be aware of these types of reactions. Okay, guys, are you still with me or have I killed you already?
I'm good.
Okay.
I think we're okay. Yeah.
Okay, so this was a tough problem. For the next one, instead, you should be able to hopefully tell me everything. So I want to know how we can make this compound, of course, as a single enantiomer.
So,
And I always tend to give you important hints with the titles of the slides, so it shouldn't be too hard.
We use proline again.
We use proline again, yeah. So where can we break the molecule, guys? Thinking about what I have written in the slide title.
So would you there?
Yeah, there.
Yes, exactly. Yes. So we can break the molecule here, correct? And which would be our starting materials?
That'd be methyl group, and then
Yeah. And on the other side, what would we have?
one, two, there, like that, I think.
Okay, yes, that's correct. So we can start from these two aldehydes. Very good. 1 and 2. Excellent. Okay, so what do we do with them? We said that we will use proline, and it will be an asymmetric aldol reaction. What do we do in this case? So we have two carbonyl groups that can be attacked equally by proline. Which one do we want to react with proline first? That one, yes, great, Jack. How do we force it to react? It was specified in the video.
Do you like have a excess of it, like a 90% or something?
We can have an excess of this guy here, so that is one option. I wanted you to think about another option we may have. So we can use an excess. What else could we do, guys?
Just have them first.
Oh, could you protect the aldehyde, or like?
We can, as Will has suggested, I think we can add this aldehyde with the proline first. Okay.
Oh, it was me, but
That was Mitch.
But I'll let Will have that one.
Sorry,
No, that was Mitch.
Because my ears are closer to when I am tired aren't so good. So apologies, Mitch. I'm very sorry.
Because he hasn't got his camera on.
Yeah, so
It's actually Putin anyway. So.
Oh God, Mitch.
Okay, so we can add this aldehyde first with the proline, and then add the second aldehyde at a later stage. Okay, so what do we form between this aldehyde and proline, guys?
The enamine or aminium.
Yeah, so we form the enamine. Which one? We have two options in this case.
E.
E. Why?
Because it's less hindered with the methyl.
Correct. Very good. So we form the E-enamine. And once again, we have the formation of this 6-member transition state, which I will never ask you to draw. Okay, guys. But from here, we have that the aldol reaction becomes enantioselective. Okay, guys. So we have the formation of this final intermediate enantiomerically pure. And from here, what do we do?
You can hydrolyze the...
Correct. We just hydrolyze the amine, yes, with water, and we obtain our product, plus of course the proline, which gets recycled. And it shouldn't be too hard to see that this product here is our target molecule. Okay? All good so far?
Yeah.
Yeah? Okay. Okay. Now, I would like you to tell me how we can make this molecule. Again, you have a big hint in the slide title. And I would like you to start from this, I'm sorry, intermediate. What can we use together with this intermediate here. So this can be one of the two reagents we need. What else can we use?
An aldehyde, maybe?
Aldehyde, yes. Can you draw me the structure of the aldehyde we can use?
Maybe. How do I?
And also, can you tell me which reaction we can perform to get this final product here? So this part we already have. We need to find something we can use to insert this part here.
So you just want like a conjugate addition?
Conjugate
addition.
Great.
Reaction.
Great, Jack. So what do we need for the conjugate addition, which must be asymmetric, as we want to prepare the compound as a single enantiomer? So what can we use? So you said an aldehyde, I agree. What's the structure of this aldehyde?
Something with like a bulky group to face the right way.
So we said conjugate addition, right?
Yeah.
What else do we need in our aldehyde for the conjugate addition to take place?
A double bond.
A double bond, excellent.
Oh, okay.
Yeah.
Oh, yeah. An alpha beta unsaturated one.
So our aldehyde could be this one. Okay, guys.
Oh, okay.
So we can use these two starting materials here. And we need those something else.
Millen's catalyst.
Exactly. We can use the Macmillan's catalyst. Okay. So what happens in the reaction? Let's start from the catalyst. What does it do? It reacts with what?
The aldehyde.
With the aldehyde, yeah.
With the aldehyde. What do we form?
An aminium ion.
Yeah, the aminium.
An aminium ion, yes, which will be the trans one, okay, thanks to the presence of these two methyl groups, okay. Good. Now what happens?
So the other reagent can act as the nucleophile to attack the double bond. So the ring part, the double bond in the ring.
Yeah, you can have the lone pair from the
From here,
nitrogen.
what happens?
So with like the nitrogen, the lone pairs form a double bond to the adjacent carbon, and then the double bond can be a nucleophile.
Okay, and where does it have to attack from?
Does it attack the bottom of the double bond,
Yeah,
the bottom
attacks
closest one?
Here.
Yeah, so exactly from there. Okay, that's good. So it attacks from behind. We have these bulky groups. This is impeding the attack from the front. Okay, guys. While these other groups are impeding that it attacks here. So it has to attack in this position here. Okay. So here you have all the curly arrows needed for the formation of this guy here. From here, what happens?
Oh.
So in order to show that the attack has happened from behind, I have shown this stereochemistry here for this proton. It's clear, right, guys? Yeah, good.
Yeah.
Now,
then you can
so do we have to hydrolyze it?
Yeah, hydrolyze it with water.
Okay, so what happens first? So is this situation something that will stay as drawn in this way, guys? Or
so will the proton on the this one?
Yeah.
Here.
Okay.
Oh, deprovents.
Okay. So we have the formation of this intermediate here. So from here, what happens? You have just said it. We have the hydrolysis with the removal of our catalyst. Okay, guys. So if we rotate and redraw, it should be easy to spot that we have the desired configuration at the chiral carbon. Okay, and from here, what do we do?
Oxidize the
Yeah,
aldehyde.
oxidize the
Yeah.
aldehyde.
What could we use for this oxidation?
Permanganate.
Yeah,
Yeah.
permanganate would work. Yes, absolutely. Okay, so just to give you an information, for this specific COX inhibitor, this catalyst has been optimized, so with the terbutyl group, which improves the yield with in a correct enantiomeric excess of the reaction. Okay, okay, so time for our breakout room. Okay, guys, so you will have, which I will send it in the chat in a moment, 2 slides for this breakout room, and I would like you to try and fill the boxes with the different intermediate products for this reaction. And in the end, I would like you to find out how proline can be used in order to synthesize S amino acids. Okay, so let's see if I manage to stop sharing before showing you. No, unfortunately no. So I need to be quick. Okay, so I'll stop sharing and I'll send you the file as always. And you please tell me if you receive it fine. So that's organocatalysis today, breakout room. Okay. Okay, can you see if you can download it fine, guys? Please.
Yeah, I think it's
Yeah.
good.
Okay, excellent.
So
Yeah, that's the
two
one.
two slides.
So with the 2 slides of boxes to fill, and there's just a few of us today. So we'll create only 4 groups.
Should we do both slides?
Yes, if you can, yes. And I'll be generous. I will give you 8 minutes today as you have 2 slides. And okay, so
We only need 5.
hopefully so. I'm not sure, but maybe. Maybe. Okay. Bailey, Reese, and Adam, do you have issues? Only Bailey and Adam. To join the breakout room? Okay. Okay, are we all back? I think so. Yeah, no, maybe one person is missing. Maybe they left. Okay. How was it?
Kind of tough.
Tough? Okay. Do you have any ideas?
It's an okay film.
And okay?
Let's
Misbehave.
Did you sort it
Just making
out?
a bad joke.
Fine, Mitch. Okay, let's share my screen once again and let's see what you think. Okay. Okay, so first stage shouldn't be too hard. What?
Deprotonate the proline.
Okay, so what happens here? We are treating in acidic conditions using an alcohol. So what do you think happens?
Make an ester.
Make an ester, yes, Sophie, that's excellent. We make the methyl ester on the carboxylic acid, okay? Then here I have specified this amide coupling because I'm not sure how much you have seen about amide coupling already or how much you remember, okay? So what do you think happens? What are we referring to when we say amide coupling?
That the carboxylic acid making a bond with the nitrogen.
That's correct. Yes, that's correct. Very good, Sophie. So we make an amide between this amine and our carboxylic acid. Very good. And these DCC and HOBT are just some very common coupling agents which are used very often with chiral molecules in order to avoid harsh conditions and not risk to have racemization or epimerization at chiral centers. Okay? Okay. Good. So from here, what happens? We have ammonia in methanol. What may happen?
So we make is the other ketone part turned into an amine? The other oxygen.
Oh, sorry. Which one? Sorry. I got it wrong,
that one.
Jack. No, it's not that one. We have something else. Anyone, guys? Yeah, there. What happens there, Jacob? So we have an ester. What happens if we treat with ammonia?
The amine just attack there. Like.
The amine attacks there, yes. And what do we form?
Amide.
Amide. Very good, very good. We have the formation of this amide, and I have highlighted the lone pair there for you guys. What do you think it may do?
Intra.
Intra, yes.
Intra. So I'm guessing a rings form. So the ammonia.
So where can it attack? Yes.
The ketone right below it. Then yeah.
The ketone right below. Okay.
I don't know why we're laughing.
That's good. Okay. So here we create a new stereocenter, but the chirality here is not relevant. Okay. So we don't care about it that much. Okay. Okay. Now we are using, strong acid. What could it do? It's nothing exotic.
Protonate?
Protonate, yes.
Dehydrate the...
Protonates this oxygen, okay? So the acid just protonates the oxygen there. Now from here, what happens? What could happen? Once again, you have a hint.
Could the lone pair come in to make a double bond and that kicks out the water?
Exactly. So we eliminate a water molecule. That's great. With the formation of this intermediate here. What happens from here?
Could that proton go up, then the double bond goes back into the nitrogen? So you...
Yeah, that's correct.
Yeah.
Very good. And we are in this situation now. What happens? Let's think about our reagents here, so it shouldn't be tricky.
I'll just reduce the double bond.
Yeah. It reduces
hydrogenate the double bond.
Yeah, hydrogenation there. Yes. So the only special thing about this hydrogenation is that it is enantioselective due to the molecular shape of the substrate. Okay, it is slightly folded, so the PD catalyst has to interact with the outside surface, adding the hydrogen only from one face. So we have an enantioselective hydrogenation. Okay, and from here we just hydrolyze our proline and we get our S amino acid. Okay, all good, guys? Okay, so if you can be strong, we can do just a couple of extra exercises, just 2, okay? And then I will leave you a few more on Canvas.
So that hydrolyzes both amides at the same time.
Exactly.
Okay.
Okay. So we have said in the second video for today that carbenes are organocatalysts, but they are moisture sensitive, so we need to perform the reactions which involve these N-heterocyclic carbenes under inert atmosphere. Because they are moisture sensitive, they react with water. Can you tell me why, guys?
So that double bond will try and take a proton. It's very basic.
Okay, so we have the formation of a hydrogen bond to start with, yes. And we have this situation here. So you're right, Jack, it wants to take up this proton. And so what happens from here? Exactly what you said. We take the proton and we release hydroxide. Correct? And now?
Would the hydroxide just want to take it back again?
What could this do?
Could that attack the carbene? Yeah.
Attack. Yeah. So we can attack this carbon here, okay, with the formation of these intermediate species. Okay, guys.
It just hydrates still. So.
Did you say it hydrates again?
Well, yeah, could.
Yes, it does. Okay, so here we have this kind of situation, okay, guys, operated by a second molecule of water, okay, with basically the formation of this open ring, okay? And this is why we need to keep N-heterocyclic carbenes away from water, okay? Are we still alive?
Yeah.
Okay. So, okay, last exercise, but then I will leave because I had a few extra prepared for today, but I can tell that you are destroyed, so I won't be cruel. I will leave 2 or 3 more exercises with my slides on Canvas, okay, guys? Please have a look. Okay, I would like you to tell me the mechanism for this reaction. So tell me what happens.
So does the carbene attack the aldehyde?
Yeah, the carbene attacks the aldehyde. So you have seen in the video already that when this happens, we have the formation of this imidazolium alkoxide species. Okay, can we draw it in another way?
So yeah.
Mm,
So with that and there,
yeah,
then that goes up there, so that you have the negative. So then you have like you have an OH
The
here,
lone pair on the
and
oxygen,
then
on the
you
carbon.
then you have a negative charge there.
yeah, that's great. So we have moved everything in a way that it looks like this, and this can be drawn also how? Excellent, very good. So we have that this can be drawn like this. Do you remember how it is called? It's not
Breslow.
Breslow intermediate. And can you tell me what is special about it?
It's
Oh,
nucleophilic.
umpalong, inverted.
Ampolon, that's great, very good.
Enol.
Have we seen any other recent example of that?
When we did the benzoin lab, we did use this last year, didn't we?
Have you seen something related to Ampolon?
Yeah, it was on Tuesday. Yeah.
Yeah.
I
Oh,
can't
was the
remember which one.
dithiones
Yes,
on
exactly. Very good, Jack. So
and then
we've
Bewley.
seen two very useful examples on how we can make carbonyl compounds from electrophilic to nucleophilic, so inverting their polarities, okay? And this can be quite important when you need to think about retrosynthetic strategies for a range of compounds. Okay, so we are almost at the end, guys. You can do this. So what happens now?
So now the nitrogen and lone pair can make the double bond attack the double bond of the unsaturated ketone?
Yes, absolutely. So we have this kind of situation, okay, with the formation of these species. And now
so yeah, it's good.
Okay, first we have something else.
So do we rotate the bond and then?
Not yet.
Okay.
So we have, for this reaction, we have the base that removes this proton here, but you can draw it as a proton transfer and it will be fine, okay?
Okay.
And then we have the proton transfer for this proton, okay, guys? But it doesn't matter which way you draw it, as long as you arrive to this situation here. And from here, what happens?
You make the carbene again. Or
When the bond,
Which way does it go?
to the right.
Yeah, I guess, yeah, it goes here and then.
Okay,
to the nitrogen.
excellent, very good. So we regenerate our organocatalyst, and we have the formation of this molecule here, okay, guys, that we can draw like this, okay? All good?
Yeah.
Okay, so you confirm that you are all still alive? Yeah? Okay, that's it. I won't go any longer for today, okay, guys? But you will find 3 extra exercises on Canvas, okay? So please have a look and let me know if anything sounds or looks obscure. And you will also have an unassessed workshop for ready, or it's already on Canvas. And tomorrow, if you want to have a chat to discuss anything, I'll be on Zoom from 2 to 3 p.m. Okay, guys? So have a rest for tonight, relax, and yeah.
That's right.
Hopefully.
Thank you.
Thank you.
Thank you very much, Marcella.
Thanks,
See you
Marcella.
tomorrow or next week.
Thanks,
Okay?
Marcella.
Thank you,
Bye,
Marcella.
You too.
Bye.
bye, bye, bye.